In 1957, Hugh Everett III proposed the many worlds interpretation, a radical solution that replaces wave function collapse with a branching structure, where every quantum outcome remains in the total state. Quantum decoherence, the measurement problem, the Born rule and its probability puzzles, wave function realism, Bell inequality violations. These are not science fiction premises. They are active research programs with laboratory data, Nobel laureates, and ongoing disputes. The question is not whether quantum mechanics works, it demonstrably does. The question is what it means. And one answer, refined over decades by Sean Carroll, David Deutsch, David Wallace and others, suggests that you exist in multiple versions, branching with each quantum event, separated not by distance, but by the mathematics of entanglement. What follows is a forensic examination of that claim. Not speculation, not philosophy dressed as physics. The formalism itself, the experiments, the decoherence rates, the objections, and the implications, some verified, some contested, some sitting at the boundary of what science can establish. By the end of this video, you will understand what the Everett interpretation actually claims, how decoherence produces the appearance of classical definiteness, why the Born rule remains a problem, what loophole-free Bell tests constrain, and where the genuine disagreements lie. If this channel is the kind of content you return to, consider subscribing. There is no shortcut for depth. Let us begin with what the many worlds interpretation actually asserts, stripped of metaphor, reduced to the mathematics. In standard quantum mechanics, isolated systems follow the Schrödinger equation. IH bar times d by dt of psi equals h hat times psi. This is unitary evolution, smooth, deterministic, reversible. The state vector psi changes continuously under the Hamiltonian h. No randomness enters, no information is lost. H bar is the reduced Planck constant, approximately 6.63 times 10 to the negative 34th joule seconds divided by 2 pi, or roughly 1.055 times 10 to the negative 34th joule seconds. This constant sets the scale of quantum phenomena, the scale at which wave-like behavior becomes significant for matter and energy. Measurement introduces a second rule, the projection postulate. When you measure a system, the state collapses to one of the possible outcomes, with probability given by the Born rule. Probability of outcome: I equals bra psi, p sub I, ket psi. This produces a single definite result with a probability calculated from the squared amplitude. The tension between these two rules is the measurement problem. Unitary evolution is always unitary, continuous, reversible, deterministic. Projection is non-unitary, discontinuous, irreversible in a certain sense, probabilistic. When does one rule apply and when does the other? What constitutes a measurement? Is it the involvement of a macroscopic apparatus, a conscious observer, a certain level of complexity? The formalism does not say. This is the puzzle that the famous double-slit experiment crystallizes. A single particle passes through both slits simultaneously, creating interference patterns that demonstrate its wave-like nature until measurement forces it to behave as if it went through only one slit. The wave-particle duality reveals the measurement problem in its starkest form. The Copenhagen interpretation, associated historically with Niels Bohr and Werner Heisenberg in the 1920s and 1930s, handles this pragmatically. Classical description is required for measurement outcomes, and state update is part of the rule set. The wave function is not necessarily a description of reality, it may be a tool for calculating probabilities. Measurement outcomes are definite, and the projection postulate captures this definiteness. Copenhagen leaves measurement as a special notion. It does not specify when projection occurs or what physical process triggers it. Different proponents have offered different accounts, making the Copenhagen interpretation more a family of views than a single coherent position. John von Neumann, in his 1932 axiomatic formulation of quantum mechanics, embedded the projection postulate formally. Paul Dirac, in his influential 1930s textbook, similarly presented collapse as part of the quantum mechanical rule set. This became the textbook approach, taught to generations of physicists, used successfully for calculations, but leaving foundational questions open. Hugh Everett's move, published in 1957, is radical in its simplicity. Remove the projection postulate entirely. Keep only unitary dynamics. Let the Schrödinger equation apply universally to particles, to apparatus, to observers, to the environment, to everything. What happens then? Consider a simple measurement. A quantum system exists in superposition, a ket 0 plus b ket 1. This means the system occupies a linear combination of two basis states, with complex amplitudes A and B. The amplitudes encode the weight of each component. Specifically, the absolute value of a squared gives the probability of finding outcome 0 upon measurement, and the absolute value of b squared gives the probability of outcome 1. An apparatus starts in a ready state ket A sub 0. The measurement interaction is an ordinary physical interaction that correlates the apparatus with the system. The sum over I of C minus I ket I times A0 goes to the sum of C minus I ket I times AI. The apparatus state now carries a record of the system state. If the system was in a superposition, the combined system plus apparatus is now in an entangled superposition of correlated states. This is the von Neumann measurement schema, the pre-measurement stage. System and apparatus become entangled. The apparatus is now in a superposition of different record states, each correlated with a different system outcome. In standard Copenhagen, projection intervenes here, the state collapses to one term. One record becomes definite. The other possibilities vanish. In Everett's formulation, no collapse occurs. Both terms persist. The global state contains both outcomes correlated with different apparatus records. Neither term disappears. Neither becomes more real than the other. They coexist as components of the universal wave function. Now extend this. The apparatus interacts with an observer, a scientist reading a dial, a detector logging data. The observer becomes entangled with the apparatus, which is entangled with the system. The observer now occupies a superposition of different observational states, each correlated with a different apparatus record, each correlated with a different system outcome. The observer interacts with an environment, photons scattering off the apparatus, air molecules bouncing off the observer's body, thermal radiation exchanging energy with everything. Each interaction produces further entanglement. The environment becomes correlated with the observer, which is correlated with the apparatus, which is correlated with the system. All of them together form an ever-expanding web of entanglement. What does the observer experience? This is where decoherence enters. Decoherence is not a philosophical addition. It is a quantitative physical process that has been measured, modeled, and verified across multiple experimental platforms. Decoherence stands as one of the most important developments in quantum foundations since the original formulation of quantum mechanics. Decoherence is the dynamical suppression of interference terms in reduced descriptions due to entanglement with environments. When a system becomes entangled with its environment, the local description, what you can access by measuring only the system without controlling or measuring the environment, loses the interference terms that would reveal superposition. Let me be precise about this, because decoherence is often misunderstood. A pure quantum state can exhibit interference. If you have psi equals a ket 0 plus b ket 1, you can perform measurements that reveal the superposition, experiments that show both components are present, interfering with each other. Double-slit experiments, interferometers, quantum computing gates all rely on this interference. Interference requires coherence between the components. The terms must have a definite phase relationship to interfere constructively or destructively. If that phase relationship is randomized or inaccessible, interference is suppressed. Entanglement with an environment does exactly this. When the system becomes entangled with many environmental degrees of freedom, the phase information is effectively lost to the environment. It is not destroyed, the global state remains pure and coherent. The phase information is spread across so many environmental degrees of freedom that local measurements cannot access it. The mathematics is precise. The full state of system plus environment is described by a density matrix RHO sub SE. The reduced density matrix of the system alone is obtained by tracing out the environment. RA2 sub S equals trace over E over O sub SE. This trace operation averages over all possible states of the environment, leaving only what is locally accessible. For a system in spatial superposition, the off-diagonal terms of the reduced density matrix, the terms that encode interference, decay exponentially. The decoherence equation is rho of x prime at time t equals rho at 0 times e to the minus lambda t times x minus x prime squared. Lambda is the localization rate, a measure of how quickly decoherence occurs. Lambda is enormous for macroscopic systems in ordinary environments. Let me give you numbers. These are from standard decoherence analyses, specifically from the work of Eric Hughes, H. Dieter Zeh, Klaus Kiefer, and others who developed the quantitative theory of environment-induced decoherence. Consider a dust particle, 10 micrometers in diameter, about 0.00039 inches, roughly the size of a fine grain of pollen or a red blood cell. This is small to human perception, but enormous on the atomic scale, containing roughly 10 to the 12th atoms. Imagine this dust particle in a quantum superposition with components separated by 1 micrometer, 1/10 of its own size. This is the kind of superposition that, if it persisted, would produce observable interference patterns. In air at room temperature, the localization rate lambda reaches approximately 10 to the 36th power per square centimeter per second. The decoherence time for that 1 micrometer separation is approximately 10 to the negative 28 seconds. Think about that number, 10 to the negative 28 seconds, 100 septillionth of a second, about 10 to the 25th times shorter than a millisecond, about 10 to the 15th times shorter than the time it takes light to cross a proton. In a good laboratory vacuum, approximately 1,000 particles per cubic centimeter, the localization rate drops to around 10 to the 23rd. The decoherence time rises to approximately 10 to the negative 15th seconds, a femtosecond, still inconceivably fast. A femtosecond is to a second as a second is to about 32 million years. Even in deep space, bathed only in cosmic microwave background radiation at 2.7 Kelvin, the afterglow of the Big Bang, the coldest natural environment in the universe, the localization rate is around 10 to the 6th. For a dust particle in a superposition separated by its own size, 10 micrometers, the decoherence time is approximately 1 second. Think about that number. Let it settle. A dust particle. In the emptiest environment we can imagine, intergalactic space, far from any star, far from any galaxy, with nothing but the cosmic microwave background. And even there, that faint bath of 2.7 Kelvin photons, remnants of the early universe, decoheres a macroscopic superposition in about a second. This is why we do not see macroscopic superpositions, not because of consciousness, not because of mysterious measurement, not because classical physics takes over at large scales, because decoherence, environment-induced entanglement, suppresses interference on timescales that are effectively instantaneous for any macroscopic system in any ordinary environment. The standard analysis, the simple master equation form, can be written as I d rho d t equals commutator h rho minus I lambda x commutator x rho. This combines unitary evolution, the first term, with decoherence. Induced diffusion in position basis, the second term. The decoherence term suppresses coherences between spatially separated components while preserving the total probability. Max Tegmark, in a paper that became foundational for discussions of quantum effects in biological systems, calculated decoherence timescales specifically for brain-relevant degrees of freedom. His result? Approximately 10 to the negative 13th to 10 to the negative 20th seconds. Neural dynamical times, the timescales of cognition, of action potentials, of synaptic transmission, span approximately 10 to the negative 3rd to 10 to the negative 1st seconds. Milliseconds to hundreds of milliseconds. The gap spans 10 to the 10th to 10 to the 19th fold, 10 billion to 10 quintillion times. By the time any neural process could register a quantum event, decoherence has already suppressed interference. The branches, if we are using Everettian language, have already become autonomous. The outcome is already recorded in the environment. The interference that would reveal superposition is already inaccessible. This is the part that stays with me. Not because it is exciting, because it is heavy. The implication, if you accept Everettian ontology, is not that rare special events create branches. It is that branching is the constant background condition. Every quantum event that becomes entangled with macroscopic records, and that is essentially every quantum event in ordinary environments, produces decohered branches. Not occasionally, continuously, not at special moments, at every moment. This connects to what Max Tegmark calls the level 3 multiverse in his mathematical universe hypothesis, where the many worlds interpretation represents just one layer of mathematical reality, with each quantum branch corresponding to a separate mathematical structure. Before I continue, consider what this means. Take a moment. The decoherence rates are not speculative. They are calculated from known physics, scattering cross-sections, photon fluxes, collision rates. They are confirmed by experiment. The 1996 cavity QED experiment, led by Michel Brun and Serge Haroche, directly observed progressive decoherence of mesoscopic superpositions, cat states of microwave photons in a high-quality resonant cavity. They watched interference fringes decay exactly as decoherence theory predicted. This is not philosophy. This is physics with numbers. What does branch mean in this context? A branch, in Everettian usage, is an approximately autonomous component of the universal state correlated with a definite macroscopic record in a decoherence-selected basis. The branches do not communicate, not because of a fundamental barrier, but because the entanglement with the environment makes interference recovery require reversing vast environmental correlations. This is practical irreversibility, not fundamental impossibility. In carefully controlled experiments, interferometers, cavity QED, superconducting circuits, quantum computers, interference between branches is routine. That is the entire premise of quantum technology. Quantum computers work by maintaining coherence, preventing decoherence, and exploiting interference. Every quantum computing gate operates on superposed states. Every quantum algorithm relies on the persistence of coherent branches until the final measurement. In macroscopic settings, with uncontrolled environments, the degrees of freedom are too numerous, the entanglement too complex, the reversal too demanding. To recombine branches after macroscopic decoherence, you would need to reverse the motion of every air molecule that's scattered differently, every photon that bounced differently, every vibration in every substrate, all the way back to restore coherence. This is not forbidden by fundamental law. It is forbidden by practical complexity. The parallel universes of popular imagination are not universes separated by space or energy barriers. They are components of a single mathematical object, the universal wave function, that have become dynamically autonomous through decoherence. They occupy the same space, the same matter, the same energy. They differ in the correlations in which outcome is recorded where. The mathematical structure that permits this is the linearity of quantum mechanics. If two states can exist, their superposition can exist. This is built into the formalism at its most basic level. Linearity is not an assumption that can be easily modified without destroying the predictive success of quantum mechanics. Now let us address the core objections to the many worlds interpretation. The first objection, and often considered the most serious, concerns probability. In standard quantum mechanics, the Born rule gives probabilities. If all outcomes occur, what does probability mean? This is the probability problem. It has been debated for decades and remains the central challenge for Everettian approaches. Consider a simple example. A system has two possible outcomes with amplitudes A and B, where the absolute value of a squared equals 0.9 and the absolute value of B squared equals 0.1. In Copenhagen, outcome 1 has 90% probability and outcome 2 has 10% probability. One outcome occurs. The probability statement makes clear sense. It refers to the likelihood of that one outcome. In Everett's picture, both outcomes persist as branches. One branch has weight equal to the absolute value of a squared, which is 0.9. The other has weight equal to the absolute value of B squared, which is 0.1. Both exist. Both are equally real components of the universal state. What does it mean to say one is more probable? David Deutsch, in a 1999 paper, proposed a decision-theoretic approach. He argued that a rational agent facing branching should assign credences to future branches according to the squared amplitudes, not because only one branch is real, but because that assignment is the uniquely rational response to the branching structure. The argument proceeds roughly as follows. Consider an agent who will undergo branching. Before branching, the agent must make decisions, bets, choices, plans that will affect all future branches. David Deutsch argues that certain rationality constraints, symmetry, consistency, dominance principles force the agent to weight future branches by squared amplitude when making decisions. If this argument works, it recovers the Born rule not as a statement about single outcomes, but as a constraint on rational credence in branching scenarios. The agent should care more about high-amplitude branches, not because they are more real, but because that is what rationality requires. Critics argue that this smuggles in probability assumptions rather than deriving them. The rationality constraints may already presuppose a probability-like structure. The debate continues in philosophical literature, with defenders and critics refining their arguments. David Wallace, a philosopher of physics and major modern defender of the Everett interpretation, has developed these arguments further. In his book, The Emergent Multiverse and Related Papers, David Wallace treats branches as emergent structures defined by decoherence and argues that probability emerges from rational self-locating uncertainty. Self-locating uncertainty is the idea that even if the global dynamics is deterministic, even if the universal wave function evolves unitarily without collapse, an agent can treat which future branch will I experience as a genuine uncertainty, not because the physics is random, but because the agent does not know their future position in the branching structure. This is analogous to other self-locating problems in philosophy. If you know there are multiple copies of you in different rooms, and you do not know which room you are in, you have genuine uncertainty about your location, even though all facts about the world are determined. Similarly, if branching will produce multiple future selves, you have genuine uncertainty about which future self you will become, even though all futures are realized. This is controversial. Some critics argue that there is no genuine uncertainty if all futures occur. Others argue that the proposed derivations of the Born rule fail to establish the required connection between amplitude and rational credence. Adrian Kent, in his 1997 critique against many worlds interpretations and earlier work, raised structured objections. He argued that many worlds proposals can be underspecified, not providing exact branching structures or complete postulates comparable in rigor to classical theories. Adrian Kent challenged the coherence of probability in branching scenarios. He questioned whether many worlds matches the evident physical world of single observed outcomes. Tim Maudlin, in a dedicated Many Worlds chapter published in 2019, surveyed problems including probability, ontology, and basis selection. Tim Maudlin argues that Everettian approaches face difficulties that are often understated by proponents. The probability problem is not solved to everyone's satisfaction. It remains an active area of research and disagreement. Proponents claim progress. Critics claim the progress is illusory. This is the state of the field. The second major objection concerns the preferred basis. The same quantum state can be expanded in infinitely many bases. If I write PSI equals a ket 0 plus b ket 1 in one basis, I can also write it as a different superposition in a different basis, say a prime ket plus b prime ket minus, where ket plus and ket minus are different basis vectors. Mathematically, these are the same state. Which basis defines worlds? Which decomposition gives the branches? This is the preferred basis problem. If worlds split along different bases, you get different world structures. Without a principled choice, the notion of worlds seems arbitrary. The Everettian answer invokes decoherence and einselection, environment-induced superselection. Certain pointer states are robust under system-environment coupling. They minimally entangle with the environment and produce stable macroscopic records. The pointer basis is not chosen by hand, it emerges from the dynamics of decoherence. Wojciech Zurek, a major architect of modern decoherence theory, formalized this in his work on einselection. The environment selects certain states as stable, states that correlate with definite macroscopic records, while other superpositions rapidly decohere. Position states of macroscopic objects, for instance, are robust. Superpositions of different positions rapidly decohere. This is why classical objects have positions rather than existing in position superpositions. The pointer basis emerges from the Hamiltonian, from the specific form of system-environment coupling. It is not arbitrary, it is determined by the physics of the interaction. Critics argue that this does not fully solve the problem. The emergence of worlds may rely on additional interpretive criteria beyond the bare mathematics. The decoherence selected basis is stable for practical purposes, but whether it uniquely defines worlds in an ontologically fundamental sense is debated. Some argue that worlds are not fundamental but emergent, patterns in the universal wave function that are useful for description but not basic constituents of reality. Others argue that any talk of worlds beyond the universal wave function requires additional postulates not contained in unitary quantum mechanics alone. The debate continues. I return to this point often, not for comfort, for clarity. The many worlds interpretation does not add new physics. It subtracts, removing the projection postulate. The cost of this subtraction is ontological. You must accept that outcomes you did not observe are equally real components of the universal state, dynamically isolated by decoherence. This brings us to the experimental evidence that constrains interpretation choices. Bell tests are central here. They do not distinguish interpretations that reproduce quantum mechanical predictions. All viable interpretations do that. They constrain the space of possible explanations and sharpen the disagreements. In the 1960s, John Stuart Bell developed inequalities that distinguish quantum predictions from any local hidden variable theory. The idea is this. Suppose measurement outcomes are predetermined by hidden variables that are local, that do not involve faster-than-light influences. John Bell showed that such theories must obey certain statistical constraints on correlations between distant measurements. Quantum mechanics predicts violations of these constraints. The CHSH inequality is a standard form. S equals the absolute value of EAB plus EAB prime plus E a prime B minus E a prime B prime, bounded by 2. Here, E of A and B is the correlation function for measurements with settings A and B. Local hidden variable theories predict the absolute value of S is less than or equal to 2. Quantum mechanics predicts violations up to 2 times the square root of 2, approximately 2.83. Experiments have consistently confirmed quantum predictions. The 1982 experiments, led by Alain Aspect, were landmark early confirmations. Alain Aspect used calcium atoms producing entangled photon pairs and switched measurement settings during the photon's flight, closing the locality loophole that had weakened earlier tests. Aspect's experiments had remaining loopholes. The detection loophole, low detector efficiency, meant only a subset of photon pairs were detected, leaving open the possibility that undetected pairs could have restored local realist correlations. The locality loophole was addressed, but not with the rigor later experiments achieved. In 2015, a new generation of experiments closed these loopholes. Bas Henson and collaborators at Delft demonstrated Bell inequality violation using electron spins separated by 1.3 kilometers, approximately 0.8 miles, with event-ready protocols and space-like separated measurements. The experiment used nitrogen vacancy centers in diamond, entangling distant spins through photon-mediated protocols. The event-ready design eliminated the fair sampling assumption. The kilometer-plus separation ensured space-like separation between measurement choices and outcomes. Simultaneously, Lyndon Schalm and collaborators at NIST conducted high-efficiency photon experiments. Marissa Giustina and collaborators in Vienna contributed complementary work. All three groups, using different systems and approaches, confirmed quantum predictions and Bell inequality violations with unprecedented rigor. The 2022 Nobel Prize in Physics was awarded to Alain Aspect, John Clauser, and Anton Zeilinger for their contributions to entanglement and Bell test experiments. The prize citation emphasized experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. What do these experiments establish? They rule out local hidden variable theories. If you want to maintain that measurement outcomes are predetermined by hidden variables, those variables must be non-local. Correlations must span space in ways that violate the assumptions of Bell's theorem. Bell tests do not prove many worlds. They constrain alternatives. The many worlds interpretation is compatible with Bell test results because it is a no-collapse interpretation of quantum mechanics, and quantum mechanics predicts the observed correlations. The collapse interpretation is also compatible. So is Bohmian mechanics, which explicitly embraces non-locality. So are collapse models. What Bell tests do is rule out local, realistic alternatives. If you want reality to be local, to avoid faster-than-light influences, you must give up realism in some sense, or accept that measurement outcomes are not predetermined. If you want realism, predetermined outcomes, you must accept non-locality. The Everettian can say, the correlations arise because all outcomes occur, correlated across branches with branch weights matching quantum predictions. No hidden variables are needed because no collapse occurs. The appearance of measurement outcomes is local relative to branch position. The non-locality is only apparent. It is an artifact of describing branches separately rather than describing the global unitary evolution. This is a matter of interpretation, not empirical distinguishability. The cosmic Bell tests extended the constraints further. In 2017, experiments used light from Milky Way stars to generate measurement settings. Instead of laboratory random number generators, the experiments used photon arrival times from distant stars as the source of randomness. In 2018, experiments used photons from high redshift quasars, active galactic nuclei billions of light-years away, pushing back the latest time at which setting correlations could have been established. The quasar-based test reported that any conspiracy, any pre-established correlation between settings and hidden variables would have to date back approximately 7.8 billion years ago, excluding such mechanisms from approximately 96% of the past light cone volume of the experiment. This does not prove any interpretation. It closes specific loopholes, the measurement independence or free choice loophole, making certain conspiracy-based explanations increasingly difficult to sustain. If someone wants to maintain that setting choices were correlated with hidden variables, they must explain how that correlation was established across cosmological scales and timescales. The Big Bell test in 2018 took a different approach. Approximately 100,000 human participants across the globe generated approximately 97 million binary choices over 12 hours, connected to 13 experiments across multiple laboratories. By using human-generated rather than machine-generated setting strings, it addressed concerns about random number generator modeling. If someone believes that laboratory random number generators might be predictable or biased in ways that allow local, realistic explanations, human choices provide a different source of randomness. The data continued to confirm quantum predictions and Bell inequality violations. What would you conclude from this evidence? The experiments confirm quantum mechanics. They close loopholes on hidden variable theories. They demonstrate that any realistic completion of quantum mechanics must be non-local. What they do not do is prove any interpretation. Let me now address objective collapse models, the main empirically distinguishable alternative to Everett. In 1986, Giancarlo Ghirardi, Alberto Rimini, and Tullio Weber proposed a modification of quantum mechanics, the GRW model. Instead of the Schrödinger equation alone, they added spontaneous stochastic localization events. Particles randomly collapse to localized states at a low rate, approximately 10 to the negative 16th per second per particle in the original proposal. For individual particles, this is rare, a collapse every 100 million years on average. The particle follows unitary dynamics almost all the time. For macroscopic superpositions involving many particles, the collapse rate is amplified. If a superposition involves n particles, the effective collapse rate is n times the single particle rate. For a macroscopic object with 10 to the 23rd particles, the collapse rate is enormous. Macroscopic superpositions collapse essentially instantaneously. This solves the measurement problem by modifying the physics. GRW is not an interpretation of quantum mechanics, it is a different physical theory. It predicts different behavior from standard quantum mechanics, though the differences are typically too small to detect with current technology. Philip Pearl developed continuous spontaneous localization, CSL, in 1989, making collapse a continuous rather than discrete process. Instead of sudden jumps, CSL adds a continuous noise term to the Schrödinger equation that drives localization over time. The model has two key parameters, a collapse rate and a correlation length. Lajos Diossi and Roger Penrose proposed gravity-related collapse models where gravitational effects destabilize macroscopic superpositions. The idea is that maintaining a superposition of macroscopically different mass distributions creates a gravitational instability that triggers collapse on a timescale determined by the gravitational self-energy of the superposition. These models solve the measurement problem by modifying the physics. They predict single outcomes because the dynamics produces single outcomes. The cost is adding new parameters, collapse rates, correlation lengths, and the models must satisfy experimental constraints. The constraints are tight. Interferometry with large molecules tests whether quantum superposition persists for large masses. Optomechanics, the coupling of optical fields to mechanical oscillators, probes quantum behavior at the boundary of the macroscopic. Spontaneous radiation limits constrain collapse rates by looking for X-rays or gamma rays that would be emitted if collapses were occurring. Heating constraints limit how much energy collapse events could inject into systems. Reviews of collapse models summarize the status, bounded but not ruled out in all regions. The viable parameter space is shrinking but not empty. The models remain live alternatives. This is a genuine empirical frontier. Large mass interference experiments push toward regimes where collapse model deviations from unitary quantum mechanics might become detectable. If collapse models are correct, there should be a mass scale at which quantum superposition fails. Finding that scale, or demonstrating that superposition persists to ever larger scales, would be direct evidence about the physics. The 2019 experiment by Yakov Fine, Stefan Gerlich, Markus Arndt, and collaborators observed quantum interference for molecules beyond 25 kilodaltons, masses beyond 25,000 atomic mass units, molecules with up to approximately 2,000 atoms, using a 2-meter, approximately 6.6 feet, Talbot-Lowe interferometer. This pushed the boundary of macroscopic quantumness further. Matter wave interference for complex molecules was first demonstrated with C60 Buckminster fullerene, a 60-carbon cage molecule, in 1999. That was already remarkable. A molecule with 60 atoms, each with 6 protons and 6 neutrons and 6 electrons, showing wave-like interference patterns. Each C60 molecule passes through both slits simultaneously, in a sense, and interferes with itself. The 2019 result pushed much further. Molecules thousands of times more massive than C60 with thousands of atoms. The interferometer stretched 2 meters long, requiring the molecules to maintain coherence over macroscopic distances. Even 25,000 daltons remains far from the mass scales where collapse models predict significant deviations. The boundary keeps being pushed, but it has not been reached. The experiments constrain collapse models but do not rule them out entirely. The cavity QED experiments, including the 1996 work led by Michel Brun with Serge Haroche, directly observed progressive decoherence of mesoscopic superpositions, cat states of microwave photons in a high-quality resonant cavity. By preparing superpositions of different photon number states and watching the interference fringes decay, they observed decoherence dynamics in real time, confirming the quantitative predictions of decoherence theory. Serge Haroche and David Wineland were recognized with the 2012 Nobel Prize for methods measuring and manipulating individual quantum systems, including decoherence control. Their work established the experimental techniques that allow precision study of quantum to classical transitions. Space-based proposals aim to push further. The QUESS satellite, MICEUS, launched in August 2016 at an altitude of approximately 500 kilometers, about 311 miles, demonstrated satellite-based entanglement distribution and long-distance Bell tests. By distributing entangled photons from space to ground stations separated by over 1,000 kilometers, it achieved Bell tests at unprecedented scales. LISA Pathfinder, launched in December 2015, tested precision metrology in space, the drag-free technology and interferometric methods needed for gravitational wave detection. While primarily aimed at gravitational waves, the precision achieved has implications for testing macroscopic quantum behavior in the pristine environment of space. The LISA mission, planned for 2035 with interspacecraft separations of order 2.5 million kilometers, approximately 1.55 million miles, represents the frontier of precision gravitational wave detection. The technology developed for LISA, extreme position sensitivity, isolation from environmental disturbances, could potentially be applied to tests of macroscopic quantum behavior. The broader quantum physics in space program is motivated partly by the possibility of longer coherence times, reduced environmental coupling, and cleaner tests of macro-superpositions and collapse constraints. Space offers isolation from vibrations, air molecules, and many sources of decoherence that plague terrestrial experiments. This is where the frontier is, not in philosophical debate, but in experimental design. Can we push quantum superposition to ever larger scales? Will we eventually find a scale at which it fails? Or will quantum coherence persist without limit, consistent with unitary quantum mechanics and forcing us to take seriously the implications of a universal wave function? Let me now address the multi-agent paradoxes that have sharpened interpretation debates in recent years. In 2018, Daniela Frauchiger and Renato Renner published a thought experiment-based argument in Nature Communications, sometimes called a no-go result, about self-referential use of quantum theory. The argument constructs a scenario with multiple observers modeling each other quantum mechanically and derives apparent contradictions from certain combinations of assumptions. The scenario involves nested observers, a friend inside a laboratory, a super observer outside, and then another layer. Each observer uses quantum mechanics to predict the other's results. Under certain assumptions about how to combine these predictions, contradictions appear to arise. The conclusion is not that quantum mechanics is wrong. It is that certain assumptions about single outcomes, universal applicability of quantum modeling, and consistency requirements between observers cannot all be sustained simultaneously if standard quantum predictions are retained. Different interpretations respond differently. The Everettian denies single outcomes at the fundamental level. All outcomes occur. Apparent contradictions dissolve because different observers in different branches have consistent records within their branches. The contradiction appears only if you try to combine statements from different branches as if they were in the same world. Single-world interpretations must modify other assumptions. Perhaps observers cannot be modeled fully quantum mechanically. Perhaps collapse occurs and prevents the nested modeling. Perhaps the consistency requirements need revision. The argument does not prove any interpretation. It exposes tensions in our assumptions and forces clarity about which assumptions each interpretation accepts or rejects. Czaslaw Bruckner proposed a related framework, a no-go theorem for observer-independent facts, connecting Wigner's friend scenarios with Bell-type reasoning. The argument suggests that certain natural assumptions about observer-independent facts conflict with quantum predictions in extended scenarios. Massimiliano Proietti and collaborators conducted a 6-photon experiment in 2019 that implemented aspects of these scenarios. The experiment created a physical realization of a Wigner's friend-type setup using photons as proxies for observers and measurements. The results were consistent with quantum predictions and, interpreted carefully, seemed to put pressure on certain combinations of assumptions. Interpretation requires caution. Marek Zhukovsky and Marcin Markiewicz published a critique in Physical Review Letters in 2021, arguing that pre-measurements have no results in the relevant sense, and that experimental proxies may not implement the full thought experiment semantics. They argued that the photonic observers in the experiment are not actually observers in the sense needed for the philosophical argument to go through. This is the state of the field: active debate, not settled resolution. The experiments are real. The implications are contested. Different physicists and philosophers draw different conclusions from the same data. Some aspects of this debate touch on what cosmologist Sean Carroll calls quantum immortality, a controversial implication of many worlds where observers necessarily find themselves in the branch where they survive quantum events, leading to subjectively infinite lifespans despite objective mortality in most branches. Science can describe what happens and how it happens. The question of why these rules and not others, why the Schrödinger equation, why the Born rule, why the mathematical structure that permits branching in the first place, sits beyond the reach of interferometers and Bell tests. Some questions may simply be beyond what science alone can address. Now let me address what versions of you actually means in this framework. The popular framing, every decision creates a parallel you, is a simplification that captures some truth but obscures the mechanics. Decisions are not special quantum events. The relevant dynamics is not choice in any psychological sense. The relevant dynamics is decoherence, the entanglement of quantum events with macroscopic records. Consider a choice you make. That choice involves neural processes. Those neural processes involve molecular dynamics. Those molecular dynamics involve quantum events, electron transitions, molecular conformations, ion channels opening or closing based on quantum fluctuations. Some of these quantum events have multiple possible outcomes with different amplitudes. In standard quantum mechanics, one outcome occurs with probability given by the Born rule. In Everettian quantum mechanics, all outcomes persist in decohered branches. When those outcomes become entangled with macroscopic records, when they are amplified into different neural states, different muscle movements, different spoken words, different environmental traces, decoherence suppresses interference between the resulting branches. In the Everettian picture, all outcomes persist. Different branches contain records of different outcomes. If one of those outcomes leads to decision A and another leads to decision B, then there are branches with records of A and branches with records of B. The mapping from decision alternatives to branch structure is not uniquely defined by the mathematics. Branch identification depends on coarse graining and dynamical context. There is no precise decision ledger extractable from the formalism alone. What can be said precisely is this: any event with multiple quantum outcomes that becomes irreversibly recorded corresponds, in Everettian ontology, to multiple mutually decohered post-event branches, each containing an observer record consistent with its outcome. This is a conditional philosophical implication of the interpretation, not an extra experimentally separable prediction. The statement, "There is another you who made a different choice," is a metaphysical reading of the Everettian ontology combined with a theory of personal identity. Physics supplies correlations and branch structure, approximately, not a single authoritative identity criterion. What is you? Is the person in another branch you or another person? This is not a physics question. It is a question about the criteria for personal identity over time and across branches. Different philosophical accounts give different answers. The minimalist Everettian claim is, different decohered branches contain observer records correlated with different outcomes. Whether to call those observers different versions of you, or different people, or something else, is not determined by the physics. When I first understood this, I had to stop. Just stop and sit with what it meant. Not because it changes what I can measure, not because it predicts new phenomena, because it reframes what measurement means, what outcomes mean, what I means in relation to not I. Let me now present alternative interpretations for contrast. Bohmian mechanics, the de Broglie-Bohm theory, initiated by Louis de Broglie in the 1920s and developed by David Bohm in 1952, maintains particle trajectories guided by a pilot wave. Particles have definite positions at all times. The wave function is a real physical field that guides their motion through a guiding equation. In Bohmian mechanics, there is a fact about where particles actually are. Measurement reveals that pre-existing position. The appearance of randomness comes from uncertainty about initial conditions, not from fundamental indeterminism. No collapse is fundamental. Effective collapse occurs via conditioning on actual positions. Once you know where a particle ended up, you update your description accordingly. Bohmian mechanics reproduces standard quantum predictions for non-relativistic systems. It provides a clear ontology, particles with trajectories, but at the cost of explicit non-locality in configuration space. The guiding equation produces correlations between distant particles that appear to involve faster-than-light influences. This is compatible with Bell's theorem, which requires non-locality for any hidden variable theory. It sits uneasily with relativity. Relativistic and quantum field theory generalizations face significant challenges. The non-locality of Bohmian mechanics seems incompatible with the local structure of relativistic spacetime. Various proposals exist, but none has achieved widespread acceptance as a natural extension of the non-relativistic theory. Relational quantum mechanics, proposed by Carlo Rovelli in the 1990s, takes a radically different approach. It treats quantum states and values of observables as relational, defined relative to other systems. There is no absolute observer-independent state assignment. In relational quantum mechanics, the state assigned to a system depends on what system is doing the assigning. Different observers, which need not be conscious, any physical system can serve as a reference, may assign different states to the same system, and all these assignments are equally valid. There is no single true global state. This addresses measurement-like paradoxes by denying that a single global state is primary. It raises questions about how intersubjective agreement is achieved and what the underlying ontology really is. Cubism, quantum Bayesianism, developed by Christopher Fuchs with Rudiger Schack and articulated with N. David Mermin, treats the quantum state as encoding an agent's personal probability assignments for experiences, constrained by the Born rule. It is not a direct description of objective microscopic properties. In Cubism, the wave function is not out there in the world. It exists in the agent's head, representing their beliefs about what experiences they will have. Different agents can have different quantum states for the same system, reflecting their different beliefs. The Born rule constrains these beliefs but does not describe objective properties. Cubists argue that this dissolves the measurement problem by rejecting the premise that the quantum state describes objective reality. Critics argue that Cubism sidesteps rather than solves the foundational questions and fails to explain why different agents' experiences are correlated in the ways quantum mechanics predicts. The transactional interpretation, proposed by John Cramer in 1986, describes quantum processes via time-symmetric offer and confirmation waves. A source emits an offer wave forward in time, an absorber emits a confirmation wave backward in time, and a transaction is formed when these waves reinforce each other. This provides an intuitive story for some quantum phenomena, particularly entanglement and the correlations in Bell tests, using time symmetry. The ontology and consistency in relativistic settings remain debated, and the interpretation has not achieved widespread acceptance. The consistent histories or decoherent histories approach, developed by Robert Griffiths in 1984 and later by Murray Gell-Mann and James Hartley, assigns probabilities to sets of histories when interference between them is negligible. Instead of talking about states at single times, it talks about entire histories, sequences of events through time. Some sets of histories are consistent. Interference between them is negligible, and probabilities can be assigned using standard rules. Other sets are not consistent. Interference is significant, and no probabilities can be assigned. This approach fits naturally with decoherence and is useful in some quantum cosmology discussions. Multiple incompatible consistent sets can be constructed for the same situation, and which set to use for interpretation remains ambiguous. Each interpretation has strengths and weaknesses. None is experimentally ruled out by current data. The choice between them involves philosophical commitments about what explanation requires, what ontological costs are acceptable, and what problems are most pressing. The forensic summary is this: quantum mechanics works. Decoherence is measured and quantified. Bell tests rule out local hidden variables. Collapse models are constrained but viable in parameter regions. Many worlds remains internally debated but empirically equivalent in typical regimes. The measurement problem is not solved to universal satisfaction. Let me now present the historical timeline of key developments. In 1926, Max Born introduced the statistical link between the wave function and probabilities, the Born rule, in the context of scattering. He proposed that the absolute value of psi squared gives the probability density for finding a particle at a given position. Max Born later revisited this in his 1954 Nobel lecture, framing probability as fundamental to quantum description. In 1932, John von Neumann published his Mathematical Foundations of Quantum Mechanics, formalizing measurement and state update in an axiomatic framework. The projection postulate became central to textbook quantum mechanics. John von Neumann's formulation was rigorous and influential, but it embedded the measurement problem into the foundations, leaving measurement as a special process not described by the ordinary dynamics. In 1935, Erwin Schrödinger published the paper containing the famous cat thought experiment, intensifying the macroscopic superposition tension. The cat, in superposition of alive and dead states until observed, became the standard entry point to measurement and branching narratives. Erwin Schrödinger intended the example to show the absurdity of taking quantum superposition literally at macroscopic scales. In 1935, Einstein, Podolsky, and Rosen published the EPR paradox, arguing that quantum mechanics was incomplete based on correlations between distant particles. The EPR argument became central to debates about locality, realism, and hidden variables. In 1952, David Bohm developed pilot wave theory as a realist no-collapse alternative with particle trajectories. David Bohm showed that a coherent alternative to standard quantum mechanics was possible, one with definite positions, no collapse, and the same predictions. This challenged the Copenhagen consensus that alternatives were impossible. In 1957, Hugh Everett III published his PhD thesis, Relative State Formulation of Quantum Mechanics, supervised by John Archibald Wheeler. John Wheeler wrote an assessment accompanying the publication, framing how multiple observers issues could be handled within relative states rather than by adding the conventional measurement postulate. Everett's thesis was not immediately influential. It received mixed reactions, and Hugh Everett left academic physics shortly after, pursuing a career in defense analysis. The ideas lay relatively dormant for over a decade. In 1970, Bryce DeWitt published Quantum Mechanics and Reality, strongly popularizing the many worlds framing. Bryce DeWitt's vivid presentation of branching universes, multiple copies of observers, quantum immortality captured public imagination. Much of the popular conception of many worlds traces to Bryce DeWitt, rather than Everett's more technical original. Through the 1970s and 1980s, the Decoherence program developed. H. Dieter Zeh initiated foundational work on how environment-induced dynamics produces classical appearance. Wojciech Zurek developed einselection, environment-induced superselection. Erich Hughes and Zeh produced quantitative estimates of decoherence rates for various systems. This work transformed discussions of the quantum to classical transition. It showed that the appearance of classical definiteness could be explained dynamically through ordinary quantum dynamics, without invoking consciousness or special measurement postulates. The emergence of classical behavior was no longer mysterious, it was calculable. In 1996, the cavity QED experiment led by Michel Brun and Serge Haroche observed progressive decoherence of mesoscopic superpositions. By preparing CAT states of microwave photons and watching their interference fringes decay, they demonstrated decoherence dynamics in real time. In 1999, matter-wave interference for C60, Buckminster fullerene, was demonstrated, showing quantum behavior in complex molecules with 60 atoms. This pushed the boundary of macroscopic quantumness. In 2003 and 2004, major reviews consolidated decoherence formalism and interpretive boundaries. Wojciech Zurek's review in Reviews of Modern Physics and Maximilian Schlosshauer's review clarified what decoherence does and does not solve. They emphasized that decoherence explains the suppression of interference and the stability of classical records, but does not by itself select a unique outcome. The interpretive question remains open even with decoherence understood. In 2015, loophole-free Bell tests were reported. The Henson experiment with electron spins at 1.3 kilometers, the Schalm experiment with high-efficiency photons, the Giustina experiment, all closed the major loopholes simultaneously, confirming quantum predictions with unprecedented rigor. In 2016, the Messier satellite launched, demonstrating satellite-based entanglement distribution and long-distance Bell tests. In 2017 and 2018, cosmic Bell tests used starlight and quasar light to generate measurement settings, addressing measurement independence loopholes. The Big Bell test used human choices from 100,000 participants. In 2018, Daniela Frauchiger and Renato Renner published their thought experiment highlighting tensions in multi-agent quantum scenarios. In 2019, matter-wave interference was demonstrated for molecules beyond 25 kilodaltons using a 2-meter Talbot-Lau interferometer. The 6-photon Wigner's friend experiment was conducted and widely discussed. In 2021, Marek Zhukowski and Marcin Markiewicz published their critique of Wigner's friend experiments. In 2022, Alain Aspect, John Clauser, and Anton Zeilinger were awarded the Nobel Prize in Physics for their pioneering work on entanglement and Bell tests. Through 2021 to 2023, major reviews summarized collapse model constraints, quantum decoherence frontiers, and the Quantum Physics in Space program. The field continues. Multi-agent paradoxes remain active research areas. Space-based proposals advance. The interpretation debates persist. What are the limits of this inquiry? Practical irreversibility from environmental entanglement is a limit, not a tragedy. The decohering environment typically involves vast numbers of degrees of freedom. 10 to the 23rd air molecules, 10 to the 30th thermal photons. Reversal would require controlling all of them with perfect precision. This is infeasible in macroscopic settings. This is why interference between record branches is not observed outside carefully controlled experiments. Not because it is fundamentally forbidden, but because it is practically impossible. The impossibility is not mysterious. It is the same reason you cannot unscramble an egg or reverse a burning match. Thermodynamic irreversibility and decoherence are intimately connected. Measurement independence and locality constraints rely on assumptions. Even loophole-free experiments specify which loopholes are closed and which modeling assumptions remain. No experiment is assumption-free. Modern experiments close the most significant loopholes simultaneously, but total certainty is not achievable. Scale limitations exist. Moving from molecule scale to truly macroscopic spatial superpositions of objects you can see with your eyes, separated by distances you can perceive, requires extreme isolation, cryogenics, and precision control that push current technology to its limits. This is why many proposals target space platforms or long freefall times, where some environmental couplings are reduced. The speed of light signaling constraint remains. Branching narratives do not provide a signaling channel. You cannot send information to your other branches. Decoherence does not create communication between outcome branches. The branches are dynamically autonomous precisely because interference is suppressed, and interference is what would be needed to recombine or communicate between branches. And finally, the statement, "there is another you," is a metaphysical reading of the Everettian ontology combined with a theory of personal identity. Physics supplies correlations and branch structure, approximately, not a single authoritative identity criterion. Science can describe branching-like structure. The you-ness across it is not a physics parameter. The many worlds interpretation, the relative state formulation, the Everettian framework, quantum decoherence, the measurement problem, the Born rule. These are names for a research program that keeps only unitary dynamics and asks what follows. What follows is not a comfortable answer. It is not an answer at all in the sense of resolution. It is a structure, a mathematical structure with interpretive commitments that some physicists accept, some reject, and many remain uncertain about. The Born rule remains a puzzle. The probability of outcome I equals bra psi, p sub I ket p psi. Y-squared amplitude tracks experienced frequencies in a branching ontology is debated. Decision-theoretic approaches exist. Symmetry-based approaches exist. Critiques of both exist. Science describes how to compute probabilities. Why they work this way is an open interpretive problem. Branch definition remains approximate. Decoherence yields approximate autonomy and stable records, but there is no unique, exact branch counting rule extracted from the formalism alone. If you ask how many branches exist, the formalism does not give a definite answer. Branch identification depends on coarse graining and dynamical context. Science can compute decoherence rates. It does not uniquely fix a world ledger. Outcome uniqueness versus description remains contested. Decoherence produces an improper mixture in reduced states while global superposition persists. The reduced density matrix looks like a classical mixture. Like one or the other outcome has occurred, you just do not know which. The global state remains a pure superposition. Science can predict all correlations. Whether one outcome is fundamental or emergent is not decided by decoherence alone, the many worlds interpretation. Hugh Everett. Quantum decoherence. The Born Rule. Bell tests. Collapse models. Wave function realism. The measurement problem. These remain the nodes of an ongoing investigation, not a completed theory, but a framework under construction. The horror, if there is horror, is not in the strangeness. It is in the precision. The decoherence rates are calculated. The Bell violations are measured. The interference fringes are observed. And still, the question of what it all means, what is really happening when a quantum event is recorded, remains open. The unsettling verified point is not mystical choice. It is that the mathematics of unitary evolution plus entanglement naturally generates multiple outcome-correlated terms, and decoherence makes them dynamically autonomous for all practical purposes. A hard number pause. Max Tegmark's reported decoherence estimates imply that any warm, wet, macroscopic information processing system will lose phase coherence over timescales unimaginably shorter than cognition timescales, so branch autonomy in an Everett reading is not a rare event, but a constant background condition. A forensic pivot. Bell tests and their loophole closure arms race do not prove many worlds, but they aggressively restrict what a single-world realist completion can look like, sharpening the interpretation conflict into a constrained design space. A limit pivot. Decoherence explains how classical records stabilize, but not why one record is the only real one. Unless one adds a collapse mechanism or chooses an interpretation where one real record is not a primitive requirement. And here we are, brief, small, calculating localization rates and tracing density matrices, uncertain whether the mathematics we use describes a single world that collapses, many worlds that branch, trajectories guided by pilot waves, or something we have not yet conceived. The many worlds interpretation proposes that every quantum outcome remains in the total state. The evidence neither confirms nor refutes this. The formalism permits it. The ontology accepts it. The experiments are consistent with it. The version of you that did not watch this video, that made a different choice, took a different path, exists, if Everett is right, as a component of the universal wave function, decohered from the branch you occupy, inaccessible by any operation you can perform. Not across space, not in a parallel dimension, right here in the mathematics, separated by the inexorable accumulation of environmental entanglement. That is the claim. Whether to accept it is not a physics question. It is a question about what you require from physics, explanation, prediction, ontology, meaning. The Planck time, approximately 5.39 times 10 to the negative 44th seconds, is the natural unit of time in quantum gravity, formed from fundamental constants. Compare this to decoherence times, 10 to the negative 28th seconds for a dust particle in air. Even decoherence is slow compared to the Planck scale. Decoherence is unimaginably fast compared to anything we can perceive or measure directly. The LIGO interferometers, with 4-kilometer arms, approximately 2.5 miles, achieve displacement sensitivities of 10 to the negative 19th meters. This is a fraction of a proton diameter. The precision of modern physics is extraordinary. And yet, the interpretation question remains. The equations work. The experiments confirm. The interpretation remains. The Many Worlds Interpretation, Hugh Everett III, Quantum Decoherence, The Born Rule. Bell tests by Alain Aspect, John Clauser, Anton Zeilinger. Collapse models by Giancarlo Girardi, Alberto Rimini, Tullio Weber. Space-based tests with Micius. Molecule interference with 25,000 Dalton molecules. Loophole-free experiments with electron spins at 1.3 kilometers. These are the nodes. These are the evidence. These are the constraints. The measurement problem, the tension at the heart of quantum foundations, crystallized in the early days of quantum mechanics. By 1930, the mathematical formalism was largely complete. The Schrödinger equation described wave function dynamics. The Born rule gave probabilities. The projection postulate described measurement outcomes. The relation between these pieces was unclear. Niels Bohr, at his institute in Copenhagen, developed what became known as the Copenhagen interpretation, though this term encompasses a range of views rather than a single doctrine. Niels Bohr emphasized complementarity. Quantum systems exhibit different properties depending on the experimental arrangement. Wave and particle aspects are complementary, not contradictory. The measuring apparatus must be described classically, and quantum mechanics applies to the relation between classical descriptions of preparations and outcomes. Werner Heisenberg contributed the uncertainty principle and the idea that quantum mechanics describes knowledge rather than reality directly. The wave function collapse was sometimes presented as an update of knowledge rather than a physical process. These philosophical elaborations did not resolve the technical puzzle. If unitary dynamics applies always, why do we see definite outcomes? If collapse is real, when does it occur? If collapse is epistemic, what physical process produces single outcomes? Einstein, famously, was unsatisfied. His debates with Niels Bohr through the 1920s and 1930s probed the foundations repeatedly. Einstein sought a more complete description, hidden variables that would restore determinism and locality. The 1935 Einstein-Podolsky-Rosen paper argued that quantum mechanics was incomplete, based on correlations between distant particles that seem to require either faster-than-light influences or predetermined values. Bohr's response emphasized that quantum mechanics must be understood holistically. The entire experimental arrangement determines what can be said about outcomes. Einstein remained unsatisfied until his death in 1955. The EPR argument lay somewhat dormant until John Bell's work in the 1960s transformed it from philosophy to physics. John Bell showed that the question had empirical content. Quantum predictions for certain correlated measurements differed from any local hidden variable theory. This could be tested. The testing began slowly. John Clauser's experiments in the 1970s confirmed quantum predictions but had loopholes. Alain Aspect's 1982 experiments closed the locality loophole more rigorously. The 2015 experiments closed both major loopholes simultaneously. Each advance in loophole closure reinforced the same conclusion. Quantum correlations violate Bell inequalities. Local hidden variables are ruled out. Ruling out local hidden variables does not determine interpretation. Many worlds, Copenhagen, Bohmian mechanics, collapse models, all reproduce the quantum predictions that experiments confirm. The interpretation question operates at a different level than empirical test. This is why the interpretation debate has persisted for nearly a century. It is not resolvable by experiment in the usual sense. The competing interpretations agree on what we will observe. They disagree on what those observations mean, on what is really happening. The theory of decoherence emerged from recognizing that realistic systems are never truly isolated. Any macroscopic object interacts continuously with its environment, air molecules colliding with its surface, photons scattering off it, thermal radiation exchanging energy, gravitational interactions with nearby masses. These environmental interactions produce entanglement. If a system is in superposition, psi equals a ket 0 plus b ket 1, and interacts with an environment that starts in state ket E0, the combined state evolves to a ket 0 times ket E0 plus b ket 1 times ket E1, where ket E0 and ket E1 are different environment states, different configurations of air molecules, different photon scattering patterns, different thermal radiation profiles. If ket E0 and ket E1 are nearly orthogonal, if the environment records which state the system is in, then the interference between ket 0 and ket 1 is suppressed in any measurement that does not include the entire environment. The off-diagonal terms of the reduced density matrix, which encode the ability to interfere, decay towards zero. The rate of this decay depends on how strongly the environment distinguishes between different system states. For spatial superpositions, the scattering of environmental particles, air molecules, photons, depends on where the object is. Different positions produce different scattering patterns. The environment becomes correlated with position, and spatial coherence is suppressed. The localization rate lambda appearing in the decoherence equation depends on the scattering cross-section, the particle flux, and the wavelength of the scattering particles relative to the superposition separation. For air at room temperature and atmospheric pressure, lambda reaches approximately 10 to the 36th per square centimeter per second, an enormous rate that ensures essentially instantaneous decoherence for macroscopic separations. For thermal photons at room temperature, around 300 Kelvin, or approximately 80 degrees Fahrenheit, the flux is lower but still substantial. For cosmic microwave background photons at 2.7 Kelvin, the flux is much lower. Yet even this dilute bath produces decoherence on human timescales for macroscopic objects. The mathematics can be cast in the form of a master equation, an equation of motion for the density matrix that includes both unitary evolution and decoherence. The simple form ID RHO dt equals commutator H RHO minus I lambda x commutator X RHO combines the two. More sophisticated treatments include multiple decoherence channels, non-Markovian effects, and finite temperature corrections. The point is that decoherence is calculable. Given the environment, you can compute decoherence rates. Given decoherence rates, you can determine how long a superposition will persist before interference becomes unobservable. This is not speculation, it is engineering. Quantum computers must be designed to minimize decoherence. Quantum error correction fights against it. Quantum experiments must control environments to preserve coherence. The 1996 cavity QED experiment demonstrated this quantitatively. Serge Haroche's group prepared cat states, superpositions of coherent states of microwave photons with different phases in a high-quality resonant cavity. These cat states exhibited interference fringes. As environmental interactions occurred, primarily through residual cavity losses, the fringes decayed. The decay rate matched decoherence predictions precisely. This was not a test of an interpretation. All interpretations that reproduce quantum mechanics predict the same decoherence dynamics. It demonstrated that decoherence is a real, measurable, quantitatively accurate physical process. What decoherence does not do, and this is critical, is select a single outcome. Decoherence transforms a pure superposition into what looks like a classical mixture, a state where you might say it's either ket 0 or ket 1, we just don't know which. This mixture is an improper mixture. The global state remains a pure superposition. The appearance of classical probability comes from ignoring the environment, not from the environment collapsing the state. Careful analyses by Maximilian Schlosshauer and others emphasize this point. Decoherence solves the problem of why interference is not observed for macroscopic systems. It does not solve the problem of why one outcome is observed rather than all outcomes persisting. To get single outcomes from decoherence alone, you must add an interpretive layer. Copenhagen says one outcome is real, and the projection postulate applies. Many worlds says all outcomes are real in different branches. Bohmian mechanics says the particle is in one branch all along, and decoherence explains why we cannot detect the others. Collapse models say actual collapse occurs through modified dynamics. The physics of decoherence is the same in all these interpretations. The metaphysics differs. Matter-wave interferometry pushes the boundary of where quantum superposition can be directly observed. The principle is simple. Pass particles through a double slit, or its equivalent, and observe interference patterns. The interference demonstrates that the particle passed through both slits simultaneously. It was in superposition. For electrons, interference was demonstrated in the 1960s. For neutrons, in the 1970s. For atoms, in the 1990s. For complex molecules like C60, in 1999. Each step pushed toward larger masses and more complex systems. The 2019 experiment with molecules beyond 25 kilodaltons used a different interferometry technique, Talbot-Lowe near-field interferometry, that is more practical for large molecules. The molecules were functionalized organic compounds, carefully prepared to be stable in vacuum and detectable. The 2-meter interferometer allowed the molecules to develop spatial coherence over macroscopic distances. The resulting interference patterns, periodic structures in the molecular distribution, demonstrated that these large molecules were in spatial superposition during their flight through the apparatus. Each molecule was, in some sense, in multiple places at once. This is remarkable. A molecule with 2,000 atoms containing roughly 25,000 nucleons and even more electrons showing wave-like behavior. The de Broglie wavelength of such molecules is fantastically small, far smaller than atomic dimensions, yet interference is observed because the interferometer is designed with appropriate spatial periods. The molecules remained coherent during flight times of about 0.1 seconds. This was achieved by operating in ultra-high vacuum, pressures below 10 to the -8th millibars, and cooling the molecular beam to reduce thermal effects. Even 25 kilodaltons is far from truly macroscopic. A human cell contains roughly 10 to the 12th daltons of mass. A human body contains roughly 10 to the 31th daltons. The gap between current experiments and everyday macroscopic scales is astronomical. Collapse models predict that quantum superposition fails at some mass scale. The GRW parameters, for example, would predict significant deviations from unitary quantum mechanics at scales roughly 10 to the 15th daltons, still far above current experimental reach, but much closer than human scales. Proposals exist for pushing further. Optomechanical systems couple light to mechanical oscillators, tiny mirrors, membranes or cantilevers, and attempt to cool them to quantum ground states and create superpositions. Success has been achieved for micron-scale objects, though not yet for superpositions of distinct positions. Space-based experiments could exploit long free-fall times and reduced environmental coupling. A satellite experiment could, in principle, prepare a superposition of a small test mass at different positions, let it evolve in free fall for extended times, and test whether quantum coherence persists. The LISA Pathfinder mission demonstrated precision control of free-falling test masses in space. The technology exists. What remains is the specific experimental design to create and verify superpositions. Why does this matter? Because if collapse models are correct, there is a scale at which quantum mechanics, as usually formulated, fails. Finding that scale would be a discovery of new physics, not just a choice among interpretations, but a modification of the fundamental equations. If, on the other hand, quantum superposition persists to arbitrarily large scales, if every experiment continues to confirm unitary quantum mechanics, then interpretations that modify the dynamics, like collapse models, are empirically disfavored, and interpretations that preserve unitarity, like many worlds or Bohmian mechanics, are correspondingly favored. The experimental program is not about proving an interpretation. It is about constraining the dynamics. The interpretive implications follow from the dynamical constraints. Eugene Wigner, in a 1961 paper, considered a thought experiment. A friend inside a laboratory measures a quantum system and obtains a definite result. An outside observer, Wigner, describes the laboratory quantum mechanically, including the friend. From Wigner's perspective, the laboratory is in superposition until he opens the door and observes the friend's result. The puzzle. From the friend's perspective, a definite result occurred when she made her measurement. From Wigner's perspective, no definite result occurred until he observed the laboratory. Whose perspective is correct? Copenhagen handles this by insisting that measurement collapses the state. The friend's measurement collapsed the state. Wigner's description of a superposition is incorrect. Copenhagen does not specify what constitutes a measurement that triggers collapse. Many worlds handles this by denying single outcomes. From one perspective, the friend obtained result 0. From another perspective, result 1. Both perspectives exist in different branches. Wigner, observing the laboratory, becomes entangled with these branches and subsequently exists in both. The Frauchiger-Renner argument extends this to nested scenarios with multiple rounds of measurement and reasoning about other observers' conclusions. Under certain assumptions, that observers can apply quantum mechanics to each other. That measurement has definite outcomes and that logical reasoning is valid, contradictions appear to arise. The resolution depends on which assumption is rejected. Many worlds rejects definite outcomes at the fundamental level. Collapse theories modify the quantum dynamics so that definite outcomes do occur. Relational approaches deny that a single global state exists. Cubism denies that quantum states describe objective facts. The 2019 six-photon experiment attempted to implement aspects of this scenario. It created a physical system where photon polarization played the role of observer and friend states, and joint measurements tested correlations predicted by different interpretations of the scenario. The results were consistent with quantum mechanics. This was expected. All viable interpretations reproduce quantum predictions. The experiment did not adjudicate between interpretations. It demonstrated that the abstract thought experiment could be given physical realization, at least in a limited form. The critique by Marek Zhukovsky and Marcin Markiewicz argued that the photonic implementation does not actually capture the thought experiment's semantics. A photon polarization measurement is not genuinely analogous to a conscious observer obtaining a definite result. The philosophical argument relies on concepts like facts and observations that may not map cleanly onto simple quantum operations. This is a general difficulty with experimental tests of interpretational questions. The experiments test the mathematics of quantum mechanics. The interpretational questions are about the meaning of that mathematics. The connection between the two is not straightforward. What is true? In Everettian ontology, any quantum event with multiple possible outcomes that becomes recorded corresponds to multiple decohered branches, each containing records of different outcomes. If those outcomes affect behavior, if quantum noise in neural processes affects decisions, for instance, then different branches contain records of different decisions. What is misleading? The framing suggests that decisions are special quantum events, that branches correspond one-to-one with psychological choices, and that there is a clear count of how many versions of you exist. None of this is accurate. First, quantum events are not decisions in any psychological sense. The relevant dynamics is decoherence of any quantum superposition that gets amplified to macroscopic records. This includes quantum noise in neural processes, but it also includes quantum events in rocks, in air molecules, in everything. Most branching has nothing to do with any observer's choices. Second, the mapping from quantum branches to decisions is not well defined. Decisions are macroscopic, high-level phenomena. Quantum branches are defined by decoherence in the universal wave function. There is no precise correspondence between branches and choices. Different coarse grainings yield different branch counts. Third, there is no definite count of branches. Branch counting is ill-defined in the continuous dynamics of the wave function. Different analysts using different coarse graining schemes might assign different numbers to how many branches exist. This is not a question with a unique answer extractable from the physics. What can be said with precision is this: if unitary quantum mechanics is correct without modification, then the universal wave function is an enormously complex object containing components correlated with all quantum outcomes that have become macroscopically recorded. These components are dynamically autonomous due to decoherence. Whether to call them worlds or branches or something else is terminological. The connection to versions of you requires additional philosophy. What makes two branches versions of you rather than different people? This is a question about personal identity, not about physics. Different philosophical accounts of personal identity, psychological continuity, physical continuity, narratival identity, give different answers. Some philosophers who accept Everettian ontology resist the versions of you language. They might say, after branching, there are multiple persons with shared pasts but diverging futures. Whether to call them versions of the same person or different people depends on your theory of identity. The physics does not answer this. The physics provides a structure, branching correlated with recorded outcomes. The metaphysics of personal identity in branching scenarios is a further question. When I first understood this, that the physics underdetermines the personal interpretation, I had to stop. Just stop and sit with what it meant. It meant that even if you accept Everettian quantum mechanics completely, the question of what happens to me is not fully answered. The branching is there in the formalism. What I means across branches is not. This is humbling. We often expect physics to answer metaphysical questions directly. Sometimes it does. Sometimes it only constrains the space of possible answers without selecting among them. The many worlds interpretation is silent on personal identity. It provides a framework, universal unitary evolution, decoherence, branch structure, but leaves open the deepest questions about selfhood and persistence. Science can describe what happens and how it happens. The question of what I means in a branching universe, why there is something it is like to be in one branch rather than another, sits at the boundary of what physics alone can address. The many worlds interpretation removes the collapse postulate and retains only unitary evolution. The Schrödinger equation applies universally. Measurement interactions produce entanglement, not collapse. Decoherence, entanglement with environments, suppresses interference between macroscopically distinct components. This explains why we do not observe superpositions of everyday objects. Decoherence is quantitatively accurate and experimentally confirmed. Decoherence does not select a unique outcome. It transforms pure superpositions into apparent mixtures while preserving global unitarity. To interpret this as one outcome among many requires adding to the physics. The Born rule, the rule connecting amplitudes to probabilities, is reproduced empirically but not derived uncontroversially within Everettian quantum mechanics. Decision-theoretic and symmetry-based approaches exist, but face critiques. Bell tests rule out local hidden variable theories, but do not distinguish among interpretations that reproduce quantum predictions. Collapse models modify quantum dynamics to produce single outcomes, but face experimental constraints. The viable parameter space is shrinking but not exhausted. Space-based experiments and large-mass interferometry push toward regimes where collapse models might deviate from standard quantum mechanics. Multi-agent scenarios highlight tensions among assumptions about definite outcomes, universal quantum modeling, and consistency. But different interpretations resolve these tensions differently. The interpretation question is not fully resolvable by experiment because competing interpretations agree on predictions. The disagreement is about meaning, not measurement. And versions of you is a popular framing that captures something real, branching under decoherence while obscuring the technical details and philosophical complexities. This is where the field stands. Not resolved, not abandoned, active, constrained, and deeply contested. The Many Worlds Interpretation, Hugh Everett III, John Archibald Wheeler, Bryce DeWitt, Quantum Decoherence, H. Dieter Zeh, Wojciech Zurek, Maximilian Schlosshauer, The Born Rule, Max Born, David Deutsch, David Wallace, The Measurement Problem, Bell Tests, John Bell, Alain Aspect, John Clauser, Anton Zeilinger, Collapse Models, Giancarlo Girardi, Philip Pearl, Roger Penrose, Space-Based Tests, Misius, Lisa, Molecule Interference, Marcus Arndt, Yakov Fine, Multi-Agent Paradoxes, Daniela Frauchiger, Renato Renner, Czaslaw Bruckner. These are the people. These are the concepts. These are the experiments. The measurement problem is sometimes presented as an embarrassment for physics, a foundational puzzle that should have been solved decades ago. It might equally be seen as a sign of the extraordinary success of quantum mechanics. The formalism works so well, predicts so accurately, enables so much technology that interpretation debates are a luxury. Physicists can disagree about meaning while agreeing perfectly about calculations. This was not always possible. Before quantum mechanics, disagreements about atomic structure had empirical consequences. The debate between Bohr's atomic model and classical models was resolvable by experiment. Once quantum mechanics arrived, prediction became routine. The debate shifted from what will happen to what does it mean. Some physicists view this as a problem. They want a complete, coherent picture of physical reality, and the interpretation debates prevent this. Others view it as acceptable. Quantum mechanics is a tool for prediction, and tools need not be interpreted uniquely. The many worlds interpretation sits in a particular position in this landscape. It takes the formalism maximally seriously. If the wave function is real and evolves unitarily, then the branches are real. It pays an ontological cost, vastly more reality than we directly experience, in exchange for a simpler dynamics, no extra collapse postulate. Whether this trade-off is worthwhile depends on what you value. If simplicity of dynamics is paramount, many worlds is attractive. If ontological parsimony, not multiplying entities beyond necessity, is paramount, many worlds is extravagant. If predictive adequacy is all that matters, all viable interpretations are on par. Science can measure the decoherence rates. Science can measure the Bell violations. Science can measure the interference fringes of 25 kilodalton molecules. What science cannot measure is which interpretation is true in some deeper sense, because the interpretations agree on all measurements. This brings me to the philosophical dimension that runs beneath all of this. The interpretation of quantum mechanics touches on ancient questions. What is the nature of reality? How does our experience relate to what exists? Is there a single objective world, or is reality somehow perspective-dependent? Many Worlds says reality is the universal wave function, a vast mathematical object containing all quantum outcomes. Our experience corresponds to one branch among many. The single objective world is not our experienced world, it includes everything. Copenhagen says reality is described by quantum states relative to experimental arrangements. The single objective world is the classical world of measurement outcomes. Quantum mechanics is a tool for predicting those outcomes. Bohmian mechanics says reality includes both particles with definite positions and a guiding wave function. The single objective world is the configuration of all particles. Quantum mechanics describes how particles move. Cubism says quantum states describe agents' beliefs about their experiences. Reality is what agents experience. Quantum mechanics is a logic for managing expectations. Each interpretation answers the classical questions differently. What exists? What is objective? How does experience fit in? These are not empirical questions in the usual sense. They are not even straightforwardly scientific. They sit at the boundary of physics and philosophy, where methodology itself is contested. Some argue that interpretation is merely verbal, different ways of talking about the same physics. Others argue that interpretation matters deeply, that our understanding of reality is at stake. The debate about whether interpretation matters is itself a debate. What I can say with confidence is this: the mathematics works, the experiments confirm, the technology functions. From quantum computers to MRI machines to lasers, quantum mechanics enables the modern world. Whatever interpretation is true, the formalism is reliable. And perhaps that is the practical takeaway. Whatever your views on branching, whether you think multiple versions of you exist in some meaningful sense, or whether you think versions of you is a misleading metaphor, the physics is the same. The predictions are the same. The technology is the same. The interpretation question is deep, but may have no empirical answer. And that is itself a statement about the nature of scientific knowledge. Let me return to the numbers one more time. The Planck time is approximately 5.39 times 10 to the negative 44th seconds. This is the natural unit of time formed from fundamental constants, the speed of light, the gravitational constant, and the Planck constant. It is unimaginably short. No physical process we know of operates on this timescale. The decoherence time for a dust particle in air is approximately 10 to the negative 28th seconds. This is 10 to the 16th times longer than the Planck time, an enormous ratio, yet still utterly beyond human perception. 100 septillionth of a second. The decoherence time for that same dust particle in cosmic microwave background radiation is approximately 1 second. This is 10 to the 28th times longer than in air. The ratio spans 28 orders of magnitude, from essentially instantaneous to human graspable, depending on the environment. Neural dynamical times span approximately 10 to the negative third to 10 to the negative first seconds. Decoherence times for brain-relevant degrees of freedom span approximately 10 to the negative 13th to 10 to the negative 20th seconds. The gap is at least 10 billion-fold. The arm length of LIGO is 4 kilometers, approximately 2.5 miles. The arm length of the planned LISA mission is 2.5 million kilometers, approximately 1.55 million miles. The ratio is approximately 625,000. The highest mass at which quantum interference has been observed is approximately 25 kilodaltons, approximately 25,000 atomic mass units. A human body has mass approximately 70 kilograms, approximately 42 trillion daltons. The ratio is approximately 2 times 10 to the 27th. The separation achieved in loophole-free Bell tests is approximately 1.3 kilometers. The separation achieved in satellite-based entanglement distribution exceeds 1,000 kilometers. The separation implied by quasar-based Bell test settings spans billions of light-years. These numbers define the experimental landscape. They define what we can measure, what we have measured, and what remains beyond current reach. The many worlds interpretation makes no predictions different from standard quantum mechanics for any of these experiments. That is both its strength. It preserves the empirically successful formalism, and its weakness. It cannot be distinguished experimentally from alternatives. The collapse models do make different predictions in principle. They predict that quantum interference will fail at some mass scale. Finding that scale would be a discovery. Not finding it, as we push to ever larger masses, constrains collapse models and indirectly favors interpretations that preserve unitarity. The experiments continue. The mass records will be broken. The loopholes will be closed further. The precision will improve. And the interpretation question will persist, because it operates at a different level than empirical test. The competing pictures agree on observations. They disagree on reality. There is a version of you for every possible decision. That is the claim. Whether to accept it is not settled by any experiment we can perform. Whether to call those versions by that name is not determined by any physics we know. What is determined is this: quantum mechanics works. Decoherence explains the absence of macroscopic interference. Bell tests rule out local hidden variables. The formalism predicts with extraordinary accuracy. The rest is interpretation. The rest is meaning. The rest is what we bring to the mathematics, not what the mathematics dictates. And here we are, brief, small, calculating wave functions and tracing density matrices, uncertain whether we inhabit one world or many, whether our choices branch or resolve, whether the silence of definite experience hides a multitude or reveals a singularity. The many worlds interpretation proposes that every quantum outcome remains in the total state. The measurement problem asks why we experience single outcomes. Quantum decoherence explains why interference is not observed. The Born rule connects amplitudes to probabilities. Bell tests constrain hidden variables. Collapse models modify dynamics to produce collapse. The Schrödinger equation governs unitary evolution. Hugh Everett removed the projection postulate. John Wheeler supported the thesis. Bryce DeWitt popularized the name. David Deutsch proposed decision-theoretic probability. David Wallace systematized the philosophy. Adrian Kent and Tim Maudlin criticized the program. Alain Aspect, John Clauser, and Anton Zeilinger won the Nobel Prize for Bell test experiments. The Mikius satellite demonstrated space-based entanglement. LIGO detected gravitational waves with 4-kilometer interferometers. Molecules beyond 25 kilodaltons showed interference patterns. Daniela Frauschiger and Renato Renner explored multi-agent paradoxes. These are the nodes. These are the connections. These are the constraints on what we can claim and what remains open. The mathematics works. The experiments confirm. The interpretation remains. We measure distances, calculate decoherence rates, map interference fringes. What set all of this in motion and why these laws and not others remains unanswered. Some questions may simply be beyond what science alone can address. The formalism permits branching. The ontology, if you accept Everettian commitments, includes all branches equally. The experience we have is local to one branch. The gap between what the mathematics contains and what we experience is the gap interpretation tries to bridge. Different bridges lead to different destinations. Many worlds crosses by accepting ontological extravagance. Copenhagen crosses by accepting mathematical instrumentalism. Bohmian mechanics crosses by accepting non-locality. Collapse models cross by accepting modified dynamics. Cubism crosses by accepting subjective states. None of these bridges is forced by the mathematics. Each requires additional commitments beyond the empirically successful formalism. The mathematics is the common ground. The bridges are the interpretations. And the choice among bridges, that is philosophy, not physics. That is where evidence ends and argument begins. That is where reasonable people, fully informed of the data, can disagree. This is not a failure of science. It is a recognition of what science does and does not determine. Science determines what happens under given conditions. Science determines what measurements will yield. Science determines the structure of successful theories. Science does not determine what theories mean in some ultimate metaphysical sense. That determination, if it can be made at all, requires going beyond empirical adequacy to considerations of explanatory power, simplicity, coherence, and philosophical plausibility. These are legitimate considerations, but they are not uniquely fixed by data. The many worlds interpretation may be true. It may be the best account of physical reality that current physics permits. Or it may be a useful calculational picture that does not describe what actually exists. The experiments cannot decide. The arguments can only persuade, not compel. What we can say with certainty is this: whatever the interpretation, the physics works. Quantum mechanics enables technology that touches every aspect of modern life. From the semiconductors in your phone, to the lasers in your internet infrastructure, to the MRI machines in your hospitals, quantum mechanics is not speculation. It is engineering. The interpretation is speculation, in the sense that it goes beyond what measurement can verify. Whether that makes interpretation unimportant or deeply important depends on what you think physics is for. If physics is for prediction and control, interpretation is optional. If physics is for understanding reality, interpretation is essential. The many worlds interpretation offers an understanding. Whether it is the correct understanding, no one can say with certainty. And perhaps that is the final lesson. In some of the deepest questions, certainty is not available. What remains is reasoned assessment, weighing of evidence and arguments, recognition of what we know and what we do not. We know quantum mechanics works. We know decoherence is real and quantitative. We know Bell inequalities are violated. We know interference persists for ever larger molecules. We do not know which interpretation is correct. We do not know whether versions of you is literally true or a misleading metaphor. We do not know whether the universe branches or collapses or does something we have not yet conceived. This uncertainty is not comfortable, but it is honest. And honesty about the limits of knowledge is itself a form of knowledge. Not tragic, not triumphant, just unresolved. Good night.